Controls. Controls of an advanced misting humidification system. This video is an overview of those controls. I would like to say it's a detailed overview, but it's not. A detailed overview would just take too long. I may do a detailed overview, but it would be in sections. It would be in sections of the components of the controls. This system has a touchscreen display for ease of operation, but a keyboard is included for more detailed operation. This system has a PC, a personal computer, that is attached to the back of this display inside the control cabinet. The PC is manufactured by Intel with an i5 processor, 128 gig solid state drive, and 8 gigs of RAM. You could call it a micro PC, but it is a full-blown PC, and it is designed to mount on the back of monitors like this, whether it's this open touchscreen display or display that you might purchase at a computer store. It has 4 bolts that actually bolt it to the back of a display. The PC's Ethernet hardwire cable connection is connected to this particular switch right here. This switch also has a cable that goes up to a wireless Wi-Fi transmitter receiver on top of the unit. And then there is one other Ethernet cable that goes down to the Bradley MicroLogix, and it's coming into the controller right there. So the PC is reading data off of or out of this Bradley MicroLogix and displaying it on the screen. Now, I have several other videos that are on a playlist that cover a lot of the different components within this misting system. Some of those videos are input piping, output piping, bypass piping, etc. Within those videos, I talk in a small degree about the interface from the monitoring components from those sections of piping into the control cabinet here. So to get a better understanding of what I'm talking about, it would help if you watched some of those other videos. If you skip to the end of those videos, that is where I talk about control interface of the different sections of piping: input, output, and bypass. So let's get a little bit into how this unit controls. First off, the actual output capacity, the demand required for humidification, is controlled by the building automation systems, which is Johnson Controls. Johnson Controls sends a 0 to 10 volt DC signal to this control panel, which is requesting more or less humidification to the space to maintain the desired set point of 45%. You can consider that DC signal from 0 to 10 volts a 0 to 100% call for humidity or demand. Now, there are 2 other signals the Johnson Control System building automation system uses. The first one is a signal to tell the unit to run, or should we call it an enable signal, which is a input signal. The second one is an output signal from our control cabinet, from this control cabinet, and that is a common alarm relay. Anytime this unit goes into alarm and shuts down, there is a common alarm relay or a set of contacts that close that tell the building automation system that this unit has a problem and is shut down. Now, before I go too much further, I wanted to explain this picture a little bit, talk about the overall controls within the control panel. As you can see, we've got 3 sections here: top, middle, bottom. Top is the input-output section for power. Middle is the control section with microcontrollers, input-output relays, timers, and then the bottom row is input-output. Terminal strips that go out to terminal points that go out to the controls and to the solenoids. Now, mixed in, there might be a few other things, like here is the receptacle for AC power to a few power supplies, and on this control section there is a circuit breaker, or actually a fused disconnect for the variable frequency drive. Now, I have some pictures here of each set or each row power section. Yeah, am I going the right direction here? Yes, control section, microcontroller, and then the terminal strip input-output section. Now, the building automation system that we just talked about, the Johnson Controls wires, land right here in this section. And if we look at the control panel as a whole, they're right down here in the terminal strip section. So there are three sets of wires here, the 0 to 10 volts DC, and that signal is going to go into the microcontroller section, into this first I/O module of the microcontroller. The run signal, or actually we should say the enable signal, goes to the microcontroller also, but it goes up into this input section up here. It's one of these wires that is up here, and it tells the system as a whole to run. And then the third set of wires that we talked about were the common alarm relay, and from here, the landing point, they go to this particular relay right here, and that is the alarm relay, or the alarm cube relay. Anytime the system, the microcontroller, senses an alarm and goes into alarm, it energizes that particular relay. Now let's go back to the 0 to 10 volts DC input to the microcontroller and talk about that for a while. That is the heart of what makes a lot of complex stuff happen. That 0 to 10 volts is a constant live signal within this microcontroller. But that does not mean the output, the humidification supply output, the humidity output, is tracking that 0 to 10 volt signal all the time. There is a time delay built into it. We'll call it a read time delay, that at a certain point the controls will react to that read. And typically that read signal is every 30 seconds. It is adjustable, and we'll see that here in a minute, but 30 seconds is the typical setting. In other words, every 30 seconds, the microcontroller looks at the DC signal, 0 to 10 volts coming into it, and says, oh, I've got to increase my output capacity, or I've got to decrease my output capacity. We don't want the output fluctuating up and down with every little change that we have within the DC signal coming in. If you think about it, the room just does not change that fast either. It's a large room with a constant relative humidity in it, but it does have a lot of air volume, and it is bringing in a lot of fresh air. So there is change, but typically that change is quite gradual. So every 30 seconds, this controller looks at the signal and says, oh, I've got to increase my output capacity or decrease my output capacity. And it does that basically by opening the 4 solenoid valve or zone valves for the different zones of humidification. Now, I talked about this zone control in some detail in some other movies, but I'm going to go through it here very quickly. Each zone has a different number of nozzles. Therefore, each zone has a different capacity. So, zone 1, 10%, zone 2, 20%, zone 3, 30%, zone 4, 40% of capacity. Zone 4 and 1, together, 50%, zone 4 and 2, 60%, 4 and 3, 70%, 4, 3 and 1, 80%, zone 4, 3 and 2, 90%, zone 4, 3, 2, 1, 100%. Now, as the demand goes up, meaning that the DC level from the building automation system goes higher, those zone valves we just saw stage themselves on 1 through 10, 1 through 100%, every 10%. They're stage on through the microcontroller, and when they do call for a zone, some solenoid valves, they actually energize these relays right here, 1, 2, 3, 4. So these relays stage on in sequence from 0 to 100%. 10% you have one of them on, 100% all 4 of them are on. There is a little light on each one of them telling you that they are on. And when they do come on, 24 volts AC power from this transformer goes into the top of each one of these relays, and then when it comes out the bottom, it actually goes to this set of fuse blocks here. Actually, it's the 4 fuses to the right side, here to here. The other 2 on the left-hand side, one of them is an input solenoid valve, and the other one is the bypass valve. So each solenoid valve, or sets of solenoid valves, is fused. And when each one of those solenoids comes on, it lights up a little light here on the front of the display, right here. Each one of them turns red, and that is the same set of lights that you see on each one of the cube relays that we saw just a moment ago. So again, this is a good indication of the capacity output of the unit, 10%, 20%, 30%, 40%, and so on. 4 and 1, 50%, all the way up to 100%. But you also get the same thing by looking at this JCI Johnson Controls demand percentage. This is the 0 to 10 volts signal, which corresponds to 0 to 100% output. Right now it says 0.2, so it's really not doing anything. But if we were calling for 50%, it would say 50% here. And we would have lights 4 and 1 on. Now, as long as this display is up here, we'll talk about a subject that we talked about a little while ago, and that was the stage read delay. Right here it says stage read delay, and that's the 30-second delay that I talked about between reading what the actual Johnson Controls value is and what the system itself should do with that value, whether it's gone up or gone down. And then I talked about the setting to change that read delay. And if we go right here and zoom in a little closer, we can see that that setting is right here, JCI stage read delay timer. If you click on that, it'll ask you for a password. You enter the password and you can change this delay set point. Right, this one is set at 40 seconds. Typically it's 40 to 30 seconds. And then that adjustable value actually has some high and low limits. You can't just adjust it out to 10,000 seconds, and you can't adjust it any less than 10 seconds. The range is from 10 seconds to 90 seconds. That's all you can adjust it. Now the same is true with a lot of these other settings that we've talked about in the past in some past videos. They all have limits. You can't adjust them way out, or you can't adjust them, let's say, way in. There are limits to how far you can adjust them. Now let's switch gears here for a minute and talk about some other things. Let's talk about the control panel as a whole. Talk about the components that are in the control panel and talk about those components as groups. The first group we'll look at is the fuses and the circuit breakers. So there are many of them in here. First 4 here is the main circuit breaker. In fact, it's the first 3 to the right. The one to the left side is just a single pole circuit breaker that provides the 120 volts to this receptacle right here for the power supplies for the PC and for the display. So it is not tied to these other 3, even though it is next to it. These other 3 are ganged together for a 3-phase circuit breaker. By the way, that's 208 volts, 3-phase, 20 amps with a neutral. And so that breaker to the left of it is just a single pole, and it's actually at 8 amps, providing power to this receptacle. If we continue on with circuit breakers, there's a 2-pole 208 volt circuit breaker here. That actually is the circuit breaker for this transformer, the input side. This transformer is 208 volts input, single phase on the input, and then 24 volts AC on the output. The next circuit breaker, and actually it's not a circuit breaker, it's a fuse block. It's this guy right here. It looks like a fuse block. It is the fuses for the variable frequency drive. Now these fuses are going to be either 10 amps, 15 amps, or 20 amps, depending on the motor horsepower of this variable frequency drive. 10 amps, 1 horsepower, 20 amps, 2 horsepower, 15 amps, 2 horsepower, 20 amps, 3 horsepower. And the last group we're talking about is fuses, and we did talk about these a little bit. It's these 6 right here. These are the solenoid coil fuses. 4 on the left, 4 on the right are for the zone, 1 through 4 zone, and the 2 that are on the left are for the input water supply and the bypass solenoid valve. And there is one other item that similar to that, and that's the disconnect itself. It's 3-phase disconnect rated at 25 amps. Now this is a good time to mention that this panel is UL listed. It has a UL sticker over on the door here, and I'll show you a picture of that right now. And here is its UL listing. Enclosure Industrial Control Panel. It has a UL number to it. Now I should have zoomed in here a little bit so you can see things a little better, but there we go. There's the circuit breakers we talked about there, fuse block for the VFD, and then the 6 fuses for the solenoid valves. Now let's get a little more detail of this control section here, the PLC and its accessories. The PLC is an Allen Bradley MicroLogix 1100-16DWD. That's the model number. There are a variety of models of the MicroLogix 1100 and the L16, and it's the last three letters. This happens to be a DWD. There are some other letter designations that do some different things. Mainly, it's the power that comes into the microcontroller itself. Is it 120 volts, 240 volts, or is it 24 volts AC, or is it 24 volts DC? The DWD of this model happens to designate that it's 24 volts DC. Power comes in right down here, lower left-hand side. Comes from this DC power supply right here. This is 24 volts. Power supply is 60 watts. And besides powering this PLC, it does power a few other things, mainly the coils to these relays in here. There are two additional I/O modules to the right of the PLC. The first one is a Allen Bradley 1762 IF2OF2. That's the model number. The second one is a 1762 IF4. That's the second controller's model number. The first one has two analog inputs and two analog outputs, and the second one has four analog signal inputs. Those analog signal inputs come from the pressure transducers, water pressure on the output and input side, and the water flow meter, and then also the temperature sensor that is down monitoring the bypass water temperature. And this middle one here again has two outputs, and the output that actually drives the variable frequency drive actually gives it a 0 to 10 volt DC signal to tell the motor what speed it should run at. Now the next thing we could talk about is the terminal strips. Like the circuit breakers, we have groups of them, and we're going to talk about those groups. There are groups for distributing power, up here DC power, down here DC power. There are groups for distributing AC power off this transformer, 24 volts AC. And those groups are down here, 24 volt AC power. And then there are groups of terminal blocks for ground, groups of terminal blocks for sensors, input, output sensors that are down in the input and output water supply. And then finally there's a group of terminal blocks for the building automation system, the JCI system, signals in and signals out. And as you can see on these groups of terminal blocks that I just discussed, there is a color coding to them. Purple is for 24 volts AC, blue is for 24 volts DC, white is for the negative side of the DC and also for the other side of the 24 volt AC source. Green, as you can see, is ground like it usually is. Orange is signal control wires. These are the sensor control wires that go back into the Allen Bradley controllers right here and right down here. That's where those orange wires go. And these yellow wires have to do with building automation. You can see that some of them go into this I/O controller here, and actually one comes up to this alarm relay right here. It's the common alarm relay out. That yellow wire comes down to this terminal block down here. Now some of these, as I discussed, are power distribution terminal blocks. And what I mean by that is this AC terminal block here has one 24 volt AC wire coming off the power supply, off the transformer, comes down and ties to this terminal block right here. And then they're all jumpered together, and then these purple wires, 24 volt AC wires, come and go into the top of these cube relays here, which is the power for the solenoid valves. So again, 24 volts AC is solenoid valve coil power. Now the DC side, as far as those power distribution terminal blocks, there is one up here. There's 3 positive 24 volts DC and 3 negative 24 volts DC. There's distribution of DC power from there. But also, one of those wires comes down here and goes to this terminal block right here, and then from there it jumpers off and goes to other areas within this control panel. So again, these are just jumper points basically. One wire comes in and then many wires go out. And these 24-volt DC wires actually go to the bottom, which is the output of the Allen Bradley controller. You can't see that they're blue down here, but they are. They go into this controller, which has dry contacts in it, and these are the signals for a variety of components. Mainly the 24-volt DC signal that drive these relays on and off for the solenoid valves. There's also a signal 24 volts DC that gives an enable signal to the VFD, and then there's another signal when the system actually runs. It provides a 24-volt DC power out of this controller and energizes this run relay right here. This is a relay that actually does a variety of things when the system starts up. So we've covered a lot of ground here, talked about a lot of the components that are in this control panel. There are a couple of miscellaneous things we haven't discussed yet. First, this item right here. That is a temperature sensor. It's a control cabinet temperature sensor that is set at about 80 degrees. So if the internal within this control cabinet gets up to 80 or above 80 degrees, it starts this fan right here. So this is a cooling fan. It is 120 volts AC, and it is another item that comes off this circuit breaker right here, this 120 volts AC circuit breaker. The other item we haven't talked about is this time delay relay right here. It plays somewhat of a critical part of the operation of this unit, and it is only energized when the system shuts down. Now, I don't mean when the system shuts off. What I mean is when the system quits calling for humidification, gets to that point where the JCI controller says, I don't need any humidity anymore. So it's a 3-second timer, and as soon as the system quits calling for humidity, a set of contacts close for 3 seconds, and then they open back up again. And what that relay does, that 3-second relay, is it energizes zone 4 solenoid valves. It energizes those valves so any high pressure water that is left over in zone 1, because that's the last one that was on, is dumped into zone 4, and then once it's dumped into zone 4 and the 3 seconds are over with, the normally open solenoid valve, the dump side of zone 4, opens up and then dumps that residual to drain. So what it is kind of a sneaky way of dumping the high pressure water that's left over in the piping of the system before the zone valves. So it's really a safety feature. When this last zone valve right here shuts off, there is high pressure water that is trapped in this line right here back to the discharge side of the pump and the check valve. Everything else has been dumped. All zones have been dumped except for this water that's trapped in here when the pump shuts off. So what we do is when that zone 1 shuts off and the pump quits running, we open up zone 4 for 3 seconds like it is running, but it's not. Dump this high pressure water into zone 4 for 3 seconds, open it up, and then close it again, and any high pressure water that's accumulated in zone 4 then does its dump valve to drain. So this line has been reduced from pressure, and so has the dump valve on zone 4. Little complicated, a little hairy, but it does work quite well. So you'd have to think through it, listen to that a few times to understand what's actually going on. Now there's actually a little better way to do it that I'll probably implement on future systems, but it requires another solenoid valve yet. I've already got 10 in here, so what's another one? But basically it would be a T coming off here where the high pressure was, another solenoid valve, and then take it over to the dump line, which is right over here. It would be a normally open valve, closed when the system is running, and then when the system shuts down, the zone 1 has finally shut off, that valve would open up and dump any of the high pressure water that's in this line, dump it to the dump line. Also, if power was shut off to the system, meaning there was a power outage, it's a normally open valve, it would dump this particular line. That is an additional feature that I don't get when I use this zone 4 method of dumping on an off cycle. If we have a power outage when the system is running, that water is trapped in here at high pressure. It actually does slowly bleed off through through various means, but it does get trapped in here at high pressure on a power outage. And again, if I implemented that solenoid valve here to the dump line, normally open, it wouldn't do that. So that's what that timer is for right there. So that about covers it as far as the components within this control panel. What I haven't really covered is a real detailed theory of how it actually runs. What is actually going on within this microcontroller, how it is controlling this variable frequency drive, and then what is happening with this microcontroller during stages of alarms, when we get high and low pressure alarms. Now I'm going to save that for another video because it will be a lengthy video. This one is already at 25 minutes. So it's just safe to say that that will be the next video I make. A little more detail of what's going on with these microcontrollers, VFDs, and alarms. So that concludes this video. So thank you very much for listening and look forward to the next one. Talk to you later. Bye.